Hey everyone, and welcome back to the channel. Today we're diving into one of the most iconic charts in all of science, the periodic table. It might look like just a big grid of letters, but it's actually a beautifully organized map of everything that makes up our universe. So if you've ever wondered what all those squares and numbers mean, you're in the right place. Let's decode it together. First things first, let's talk about the basic layout. The periodic table arranges all the known chemical elements in order of their atomic number. That's the big number you see in each box, and it tells you how many protons are in the nucleus of one atom of that element. We start with hydrogen at number 1, then helium at 2, lithium at 3, and so on, as you move from left to right. The atomic number increases, simple enough, right? But the real genius is in how it's structured into rows and columns. The horizontal rows are called periods. As you move across a period, you're adding one proton and one electron at a time. There are 7 periods in total. Think of each period as a new energy level, or shell. For the electrons, elements in the first period have electrons in only one shell. When you get to the second period, with elements like lithium and beryllium, their outermost electrons are in the second shell, and so on down the table. So, the period number tells you how many electron shells an atom of that element has. It's a neat way to see how the electron structure builds up. Now, let's look at the vertical columns. These are called groups, or sometimes families. There are 18 groups in the main part of the table, and here's the key: elements in the same group have similar chemical properties. Why? Because they have the same number of electrons in their outermost shell, which we call valence electrons. These are the electrons that are involved in chemical bonding. For example, everything in group 1, like lithium, sodium, and potassium, has one valence electron. This makes them all highly reactive and behave in very similar ways when they form compounds. It's like they're all part of the same family, sharing key family traits. Let's take group 18 on the far right. These are the noble gases, like helium, neon, and argon. They all have a full outer shell of electrons, which makes them incredibly stable and unreactive. They're the introverts of the periodic table. They prefer to keep to themselves and don't readily form bonds with other elements. This predictability based on group placement is what makes the periodic table such a powerful tool for chemists. You can predict an element's behavior just by knowing its address, its group, and period. Now for the biggest division on the table: metals versus non-metals. If you draw a zigzagging staircase line starting from boron down to astatine, you've just separated the two main categories. Almost everything to the left of that line is a metal. That's about 75% of all the elements. Think of things like iron, copper, gold, and aluminum. What makes them metals? Well, they tend to be shiny, good conductors of heat and electricity, and they can be hammered into shapes or drawn into wires. Chemically, they love to lose electrons to form positive ends. On the other side, to the right of that staircase, you'll find the nonmetals. This group includes elements essential for life, like carbon, nitrogen, oxygen, and sulfur. In general, nonmetals are the opposite of metals. They are typically poor conductors of heat and electricity, and in their solid form, they are often brittle and dull. Chemically, they tend to gain or share electrons when they react. Hydrogen is the quirky exception. It's a nonmetal, but it's usually placed over on the left side with the metals because of its single electron. What about the elements that live right on that staircase? We call them metalloids or semi-metals. Elements like silicon and germanium fall into this category. They have properties that are a mix of both metals and nonmetals. For example, silicon is a semiconductor, which means it can conduct electricity, but not as well as a metal. This unique property is the foundation of the entire electronics industry. Your phone and computer wouldn't exist without them. They're the perfect bridge between the two major classes of elements. Let's zoom in on a few specific families to really see the patterns. We already mentioned group 1, the alkali metals. They're so reactive they'll react vigorously with water. Next to them in group 2 are the alkaline earth metals, like calcium and magnesium. They're also reactive, but a little less so than their group 1 neighbors. They have 2 valence electrons they're looking to give away. Hopping over to the other side, next to the noble gases, we have group 17, the halogens. This family includes fluorine, chlorine, and bromine. They are extremely reactive nonmetals. With 7 valence electrons, they are just 1 electron short of a full outer shell, so they are very aggressive in trying to grab an electron from another element. This is why chlorine is such a great disinfectant. It rips electrons from bacteria. And what about that big block in the middle of the table? Those are the transition metals. This group includes many of the metals we're most familiar with: iron, nickel, copper, silver, and gold. They are called transition because their properties are a bridge between the highly reactive metals on the left and the less metallic elements on the right. They are generally hard and have high melting points. What is really cool about them is that they can form ions with different charges and often form colorful compounds, which is why they're used in so many paints and pigments. So let's recap the big picture. The periodic table is not just a random collection of elements, it's a system, where every element has a specific address that tells us a story. The atomic number orders them. The period or row tells us about the number of electron shells. The group or column tells us about their chemical personality and how they'll interact with others. And the broad regions of metals, nonmetals, and metalloids give us an instant overview of their physical and chemical nature, understanding. This organization allows scientists to predict how elements will behave, discover new materials, and understand the building blocks of our world. It's a cheat sheet for the entire universe, all packed into one elegant chart. The patterns and trends you can see in the table are a testament to the underlying order of the natural world. From the reactivity of an alkali metal to the stability of a noble gas, it's all laid out for us, and that's our tour of the periodic table. It's a fundamental tool that reveals the beautiful logic hidden within matter. I hope this breakdown helps you see it not as an intimidating chart, but as a fascinating map waiting to be explored. What's your favorite element or group? Let me know down in the comments. Thanks so much for watching today. If you found this video helpful and want to learn more about the amazing world of science, please give it a thumbs up and don't forget to subscribe to the channel and hit that notification bell. It really helps us out and ensures you won't miss our next video. Until next time, stay curious.